Next, typical CAN is a peripheral. The module I am talking about, the microcontroller, otherwise a part of peripheral in the microcontroller, which is doing all this message transmission and arbitration, error detection. All these things are combined together called as a CAN controller. It is a small microcontroller element. It used to do this transmission stuff. Sometimes this CAN controller will be outside the microcontroller. Most of the microcontroller nowadays has inbuilt CAN controller. CAN controller will be like peripheral. You have to configure its clock and various register, and then you can use it. Outside your microcontroller, you will have a CAN transceiver. That is like another buffer between your CAN controller, because the voltage level will be somehow different between your microcontroller and the outside bus voltage. That's why they maintain this transceiver. After that, it is connected with the CAN A and CAN low bus. Like this only, your CAN controller will be interfaced with the external CAN bus. This is a typical diagram in which the complete CAN based ECU used to be. So that is the thing, how it is connected. Now we are coming to the core part. I believe yesterday we discussed the CAN uses the differential signal. It uses a differential signal. Why they are using differential bus? Can you give some idea why they are using differential bus in CAN? We discussed this point yesterday.
Yeah.
To reduce the noise.
Oh, brilliant. That is used to cancel the noise, in not
Yeah.
reducing. Reducing is something different from canceling. To cancel the noise. Okay. Actually, I want to transmit 0. That is my aim. To transmit 0, what I can do? I can simply bring, but 2.5 volt is the ideal, that is what to say, threshold voltage. So when you are having 2.5 volt in your bus, which means that bus is free. You are not doing any transmission. That is what its meaning. If there is no differential bus, to transmit a 0, I can bring my 2.5 volt bus value to closer to 0. 0 or 0.5 or 0.3. When I do like that, I will get 0. Forget about this red line. I want to transmit 0. That is what my aim. But actually, bus is in the 2.5 volt. It is in high voltage, which is greater than 0. 2.5 volt is greater than 0 volt. My expectation is to represent 0. Bringing that 2.5 volt closer to 0 or equal to 0 will make a 0, so that I can transmit 0. When I want to transmit 1, I can bring that back to 2.5 volt, so that I can transmit 1. But what they are doing, instead of doing like that, when they want to transmit 0, they are bringing the 2.5 volt of the CAN low signal to closer to 0. That means they are reducing its voltage and they are converging towards 1.5 volt, something like that. That will be called as 0. At the same time, they take the complement of that, the 1.5 volt, that is they are adding it, 1.1 volt. That will go up to, when we do a complement of that and you add that with a threshold, you may get some 3.7 volt, something like that. 3.7 volt, 3. Like that it will go. While they are transmitting 0, The CAN high is going from 2.5 volt to higher voltage, and the CAN low is going from 2.5 volt to lower voltage. Totally, the voltage difference will be around some 1 volt. 1 volt will be there. When you apply that to a NOT gate, you will get low. The 1 volt, 1 is equivalent 1. When you send 1 to the NOT gate, it will give 0. That's why in a bus voltage, we are able to see 0. But the 0 is going in the bus in this way. From the transmission side, when you go and connect CRO in CAN high and CAN low, you will see this waveform only. You won't see this waveform. Okay. So this is how it is going. The complement and original, both of them are going in the bus from the transmitter to receiver. Receiver will receive it, and then it will find out the difference, and then we'll send that to NOT gate, that it will get 0. Okay. Again, 1. 2.5 volt minus 2.5 volt is equivalent to 0. Again, when you send that to 0 to NOT gate, you will get 1. You may ask me a question. See, here also 2.5 volt. When you say 2.5 volt here, you are saying bus free. But the same 2.5 volt, when you say here, you are saying 1. How can I believe that? How does that one will know this is 1 and this is bus free? That is based on the startup frame. When the moment you send the startup frame, after that, when your CAN high is coming back to 2.5 volt, means you are trying to send 1. Once after sending the end of frame, that's all. After that, when you get 2.5 volt in CAN high and CAN low, which means that bus is free. Is that clear to you guys? This bit transmission, initially we will send the startup frame. After that, 0, there is a voltage variation. When it is 1, they are coming back to 2.5 volt, which is equivalent to bus free. The CAN bus will understand this as a bus free? No, it won't understand. Why? Because you send that startup frame. Till you complete it with the end of frame, they won't consider this as a bus free. Moment they get the end of frame, that's all. Okay. Now, if you have 2.5 volt in CAN high and CAN low, they will consider that as a bus free. How they are able to slice this as 0, this as 1, that is based on the sampling. When this voltage pulse is going from transmitter to reception, receiver, there is something called as the bit timing. How long it can reside in that position. They use that bit timing in the receiver side to sample these voltage pulses. They are sampling it, the bit time, that which is inverse of your baud rate. When they are sampling it, they are getting voltage variation in CAN high and CAN low, so that they consider that as 0. Again, they sample it. There's no difference in voltage. They are getting 0. If that is the case, it is 1. Again, they are sampling. They are seeing voltage variation. It is 0. Again, they are sampling. They are getting difference as 0. Then that is 1. But when they again sample it, they still see there's no difference. So these two ones, see here, for these two ones, we keep difference as 0 for a longer time. How they consider this as a 2 ones? That is based on the baud rate, the rate at which they sample. They sample it first time, they get 1. Again, they sample it, again, they are getting, there's no difference in the voltage between the CAN high and CAN low, then they consider that as a second one. Again, they are sampling, they are getting 0. Again, they sample, they get 1. Again, they sample, they get 1. Again, they sample, this time the voltage variation. Signal stays in this 3.7 high, and then this is staying in 1.2 or something like that. Again, there's a voltage variation. They are second time they are sampling, it's still in the voltage variation. Again, they sample it, they still see the voltage variation. That's why they consider this as a 3 zeros. Again, the next sample, they see no voltage variation, then it is 1. Like that only the receiver used to sample these voltage pulses which are coming with a high speed from the transmitter to receiver. They will sample it and will understand that as 1 or 0. So do you understand now how the transmitter is transmitting 1 or 0 to the receiver and how the receiver decode that as zeros and ones? Any doubt in this one? Anybody has any doubts? No doubt. How does here I moved my CAN high to higher voltage, which is closer to 5 volt, and then CAN low to, I am bringing it down from 2.5 volt to some 1.2, something like that. But I am keeping it for a long time. How does the receiver will understand this as 3 zeros? But for me, it is simply a variation from threshold voltage to a high, and then again this is now coming down. I should consider this as 1 0 only. No? All these are equivalent to 1 0 only. But they are considering that as 3 0. How?
According to bits which we are sending on.
Okay. Thank you. It is based on sampling time. There is something called as sampling time in digital electronics. When they want to sample an analog one, so let me tell you. This is my pattern. This is my sine wave pattern. I am sampling it with every, see, this is having a periodicity of some 1000 hertz. 1000 hertz. 1000 hertz. Now I have to see this pattern. I have to get this pattern digitally. Those who studied electronics have studied about digital signal processing. There will be one paper. Otherwise, people used to call as a degree stopping paper. Most of the people will fail in that one. The thing is, you have, this is your analog pattern. You want to sample it. It is having the frequency of 1000 hertz. 1000 hertz means you will have some 0.25 milliseconds, something like that. So that is the timing. 1 by 1000, what is that? 1 by 1000 is 1 millisecond. So to find out time, we will just inverse. One divided by 1000 is equal to, okay. Thank you. 1 divided by 1000. I think it is 0.0. This is 1 millisecond. 1 millisecond. 1 millisecond is the total time in which it will go from this to this stage. Now, I want to sample that. I cannot sample it with the 1000 hertz. When I sample that, I cannot get this pattern. The sampling means reading the value of the signal in different time period and then reconstructing that in the digital. what I used to do, there is a Nyquist criteria. At least I should use 2 Nyquist criteria only, I believe. I should have at least 2 into 1000 hertz. At least I should sample this with a 2K. If I sample that with a 2K, I will get 2 sample. One may be here, one may be here. Based on that, I can make a decision like I have 1 sample in the positive cycle and 1 in the negative cycle. Still, my reconstruction will be not appropriate. It will be something like this. I cannot reconstruct a sine waveform. When I go 8 sample, I will have 4 sample in the positive and 4 sample in the negative. I can able to reconstruct that. The sampling is like reading your signal value at different time period of that signal. Usually signals used to go in a particular frequency. Your sampling frequency should be greater than your original signal frequency at least 2 times. That is what the criteria that they have in the sampling. The sampling is used to find out this as 3 zeros because our sampling frequency is higher than our original signal frequency. This is your signal frequency. As per the signal frequency, it just stays in that for a long time. By the time your sampling frequency, which is having high hertz, high frequency, so it is able to take 3 samples in that time. That's why we are getting 3 zeros. It is purely based on your baud rate. That's why we have to have a proper baud rate. Your transmitter and the receiver should have the same baud rate. Then only they can exchange the information. Otherwise, in this sampling, they will get a problem. Because of that, they cannot reconstruct these zeros or ones. That is the thing. Okay, now we are going to next topic. It is clear, no? This how they are transmitting, right? This is another fashion. This is one fashion of doing transmitting zeros and ones in a physical layer. This is another fashion. Actually, when the moment the ECUs push a bit out from it and it is going in a twisted pair, means they will go like this only, either in this way or either in this way. Any one method, either this or that. You won't see 0 or 1 in the bus. We will have these pulses only. These pulses will be sampled in the receiver side and they will reconstruct from this. By sampling these pulses, they will reconstruct zeros or ones. Right now, like that only, the exchange of information happens in between each.